welcome to this MOOC course on hardware security. So, today we will be trying to introduce this topic. So, it will be the part 1 on introduction to hardware security. So, to start with, the concepts that I will be covering in today's class is trying to understand the relationship between cryptology and hardware security, trying to reflect about the advantages of hardware in security, which is in the form of developing hardware accelerators, and we will also try to discuss about like where hardware can bring in advantage in terms of security, and why hardware why security should be an important design criteria for developing hardware right from the beginning and not an afterthought. So, to start with cryptology, which is essentially I would say the more classical counterpart of computer security, it tries to aim at design and analysis of algorithms or analyze algorithms to ensure confidentiality. That means it tries to hide data from adversaries. It tries to provide integrity, that means it tries to ensure that the data is not modified by adversaries, and at the end of the day it tries to ensure that the data is available to users. So, it tries to make or ensure availability of information. So, recent days there has been tremendous growth of cryptography, which has essentially led to the development of several primitives, which tries to bring forth several interesting applications, like for example operations on encrypted databases in the cloud. It tries to develop cryptographic systems which are even resistant against the development of quantum computers, which are called in the form of post quantum cryptography. In spite of the development of cryptography, practitioners have shown that development of mathematically secure cryptographic algorithms are just the beginning. So, to quote Bruce Schneier, who is a very famous computer security expert, if you think that your problems can be solved by cryptography, then we do not understand either cryptography or we do not understand the problem. So, therefore, we need to develop tools so that at the end of the day cryptography is really realized in our systems, either in hardware or software, in a proper fashion, in a correct fashion, so that we have end-to-end security. So, one of the primary requirements of hardware in terms of making in the context of security is to address the issue that most of the cryptographic algorithms are very complex, and therefore they essentially have got a huge penalty on performance. So, we all in some form or the other are being touched upon with cryptography. For example, we are either using computing systems for e-commerce, we are using credit cards, we are doing we are essentially doing several transactions on the internet, which all in the underlying does cryptographic operations. So, therefore, the whole point is like when you are trying to accelerate these operations, then at the underlying you are doing operations through what are called as secured socket layer or SSL and transport layer, which is like a TLS, which are TLS protocols. So, if you really want to develop an open source, if you really want to understand these protocols, then OpenSSL is a very common and open source implementation of SSL and TLS, and the accompanying cryptographic algorithms like hash functions and other things like the bottleneck is that they are time consuming in software. So, therefore, if you really want to implement them on a normal CPU, then they are complex and cumbersome. So, therefore, there is a penalty in terms of clock cycles which you need to pay if you just purely rely on software. So, what hardware brings in this context is acceleration. So, you can make something which are called as cryptographic co-processors, and you can extend your current instruction set architecture or ISA to essentially offload some of your cryptographic computations on this hardware or specialized hardware. I have just enlisted here two of the very commonly known accelerators, which is in the form of what is called as AES-NI, which is a special instruction in Intel ISA for performing AES operations. And the other one is what is essentially shown here as the PCLMULQDQ, which is essentially an operation for or a specialized instruction in Intel ISA for performing carryless multiplication of two 64-bit operands. So, therefore, the advantage that hardware brings in this context is speed for sure, because it can you can develop dedicated processing, you can parallelize your operations, and therefore, you can have an end-to-end acceleration of your computation. But at the same time, it can bringing in hardware can also rule out many attacks which are otherwise possible on only pure software implementation. So, it can enhance not only speed but also security. So, let us take a look at some of these designs. For example, this is just a snapshot of an Intel AES-NI instruction, which essentially is supported in most of the modern day Intel machines, where you can actually do a round by round AES operations and you can offload them on hardware. Now, as you see in this paper, it is shown that it is a very fast design. It essentially has got something like around 53 Gbps of throughput and has been designed on a very it has been designed on 45 nanometer technology. So, this is a 2010 paper. So, it is not really so recent as of now, but it pretty much shows that using hardware you can accelerate your software operations of crypto systems, like even like the advanced encryption standard. So, I will show another case study here, which is on an elliptic curve cryptographic processor or an ECC processor. So, we will go in details about how an ECC design would be made, but at this point we can just think of or conceptualize ECC as a black box. So, ECC is a very efficient public key cipher, and in this black box, as I show here, that there are two important inputs or two inputs. One of them is the base point P, which is a point on an elliptic curve, and the other one is a scalar. Now, an elliptic curve operation is basically an algebraic operation which is done on a geometric construct, which is an elliptic curve, and finally you end up in getting what is called as a scalar product. So, this scalar multiplication is the central block of an elliptic curve processor, and therefore, we would like to accelerate this operation. If you are interested to go into a background behind elliptic curve cryptographic operation, then you can actually go through this YouTube link here, which is shown down. And but at this point, I am just trying to kind of show you that how complex these operations are. So, now there is a flavor of elliptic curve cryptographic operation which are called as characteristic 2 designs. I will be again explaining what characteristic 2 means in my following classes. So, here suppose imagine that n would be around 163 or 233 according to the standards, and I just try to enlist here the number of finite field operations which are done by your elliptic curve crypto processor. So, the number of inversions which are very complex finite field operations, again you can observe that the dimension is something as big as 233, is something like which is proportional with n and is shown exactly as 2 into n. The number of multiplication is 2n, the number of additions is 4n, number of squarings is again 2n. Now, these are all done on affine coordinates, which means that the elliptic curve point is being denoted in the usual xy coordinate system. So, if we take an Intel Core 2 Duo processor, which is an old system and with 2.93 gigahertz and an OpenSL version of 1.01c, then the average time which is required for doing 10,000 scalar multiplications is something like 8.891 seconds. So, here we show a design where, or we just comment on a design which is a hardware accelerator which is being prototyped on an Altera Cyclone 4 FPGA, which is a very popular FPGA device and a fairly low cost design, fairly low cost platform, where it will require around 4.397 seconds, which is almost like a double speed up. So, here you can see that offloading or developing a coprocessor can really help you in improving your throughput and in improving the performance of your design in general. The other important application of hardware is to enhance security. So, now we know, all of us know that our present day computing systems are naturally vulnerable against attacks. Every day, day in and day out, there are attacks. For example, we hear of several malwares hitting our systems. So, in order to understand the context and try to reflect upon why our computing systems are vulnerable against attacks, let us take a look back into our architecture textbooks and remember the famous von Neumann architecture. So, von Neumann essentially contributed to a very basic model which is called again as a von Neumann model, which essentially has got three important components. It has got a memory, it has got a CPU, and it has got an I/O component. So, the idea is that this CPU interacts with the memory and it interacts with the I/O bus. The I/O essentially talks with the external world. It is typically the keyboard or your display units. So, now the CPU essentially again it has got several blocks. For example, it has got the arithmetic logic unit, it has got the a program counter where your current address where the current address of your instruction resides, and you have got registers, which are fast form of memory. The memory in general has got a hierarchy, which means that the memory typically is slower compared to the CPU, and that brings forth what is called as a memory wall. In order to bridge that memory wall, we have a memory hierarchy. For example, we have a cache memory to sit in between between the main memory and between your CPU processing speed. So the basic paradigm of von Neumann architecture is what is called as a stored program, where the programs are also sequence of instructions which are stored in the memory like data. So the CPU typically consists of the program counter, which indicates the address of the next instruction which is to be executed, the arithmetic logic unit which performs arithmetic and logical operations, and then you have got very high speed memories which are called as registers, and you have got the control unit which basically does or interprets instructions and causes them to be executed one after the other. You have got and as I said that you have got a memory hierarchy, which means you try to bridge between the fast form of memory, the fastest form of memory, and also the you try to bridge between the CPU, which is slower in terms of processing speed, and also between your slow memory or the RAM. So now when we talk about the memory, right, which is essentially which stores the instructions, data, and the intermediate results, then it has got a several hierarchy where the registers have got the highest level and has got the fastest, another fastest form of memory. Likewise, right, you have got the input and output block which transmits and receives results and messages or information from and to the outside world respectively. However, there are several bottlenecks of the von Neumann architecture. For example, if I give you this and this bottleneck arises because of the fact that both memory, both data as well as the code resides in memory, and therefore, how do you know that whether 0x90 ABCD, for example, which is a funny looking number, is whether it's a code or whether it's a data. Now the operating system or the OS essentially has got no way to distinguish between whether it's a code or whether it's a data, because of the and therefore, right, you essentially can have malwares which can freely execute in your systems. On the other hand, because of the shared memory bus, there is a bottleneck which is called as a memory wall, and in order to bridge the memory wall, we have got several artifacts in computing architectures in the form of cache memories, branch predictions, and so on. Many of these attacks actually target this presence, like the presence of the cache memory or the presence of the branch predictions, and therefore it is fundamentally kind of arises because of the fact of because of the von Neumann architecture. So here is a very simple depiction of an attack which is a purely software attack, which is called as a buffer overflow. It may be pointed here that buffer overflow till now remains as one of the most popular forms of software attacks. So this attack here has been shown here, has been made of two program or two function calls. One is the main function call, and there is another function call which is called function, and has been written in C. So you can observe that here in the main function there is an integer variable b which is being kind of defined as b equal to 0. Then there is a call to the function call function, and then followed by a b equal to 1 assignment, followed by a print of a b of b. So since the call function doesn't affect b, what I would expect is that b should be printed as 1. On the other hand, what we will see is that because of some certain operations here in the call function, which it kind of skips this b equal to 1 line and therefore prints b equal to 0. So therefore the program does a wrong computation. So this attack has been shown in the paper which is shown here as smashing the stack for fun and profit, written under the pseudonym of Aleph1. So in order to understand the working of the attack, let us take a look at the stack. So the stack essentially stores the corresponding data as shown here. For example, it stores 12 bytes for buff, and you can see that if you go back to the code, there is a buff is an integer variable. It's an integer array of size 3, and if we assume that 4 bytes have been allocated, so this is done on an old machine of mine. So if we see that 12 bytes have been allocated for buff, then there is then I have allocated like say 4 bytes for the integer pointer, so it is another 4 bytes, and that is followed by the frame pointer, which again takes another 4 bytes. So if you take the relative distance between this point, like the buff, the starting point of buff to the return address, then it is something like buff plus 20 points to the content in the stack where the return address is stored. So now that essentially explains this line, which shows us that do an we basically increment buff or the starting location of buff with 5, and therefore we basically access the return address. So therefore int star RET therefore points to this return address. So what we do next is that we increment the value of the return address by 7. So now why 7? In order to understand that, we can take a look into the GDB dump, and here is a portion of the GDB dump which shows that this is the line which has been highlighted in red is the line which I would like to kind of skip, because here is where B becomes or B gets assigned to 1. In order to skip this line, we observe the difference between these addresses which have been shown here as 0x080483FF and 0x0808048406. So this difference is 7. So therefore what we try to do is, in order to skip this line, we increment this by 7, and therefore what happens is that rather than returning to this line, the program returns to the next line and therefore skips the B equal to 1 assignment, and therefore B equal to 0 gets printed. Now here this is a very simple illustration of a buffer overflow attack, but you can probably imagine that there can be stronger forms of attacks which one can mount. For example, one can change the return address to point out to an address where a malicious program or malware is located, and that can lead to the triggering of a malware in a normal computing system. So in order to alleviate this software only attack, we essentially can bring in hardware. So for example, one of the popular approaches which people can do is they can try to implement a hardware stack. So what we did in one of our works is trying to implement a hardware stack such that whenever it encounters a JALL, which is a jump and link, which is a common jump instruction, and similarly other instructions, what we try to do is we try to maintain a hardware stack. We try to kind of develop custom instructions where a hardware stack gets enabled or it gets disabled, where we freeze the hardware stack or we unfreeze the hardware stack. But the idea is that we try to see that whenever the buffer overflow tries to modify the return address, which is probably stored in some which is stored in some value, then what happens is that rather than taking the value from the software stack, the data is being taken from the hardware stack, and therefore the damage that the software attack is doing remains inconsequential. So in this work, which we prototyped on an open RISC platform, where the register R9 is essentially is where the return address gets located. So whenever the hardware stack encounters a J.R, whenever we encounter a J.R instruction, then with register R9 as a parameter, it pops its top value and therefore passes that as a return address rather than what is being actually stored in the software stack. So therefore, with this simple incorporation of a hardware stack, we can actually and also of course incorporation of these dedicated instructions which are shown here as custom 7, custom 8, custom 1 and custom 2, we can actually alleviate the effect of a buffer overflow attack on our software. The other point which I would like to mention is that which I tried to hint upon is that because of the memory wall, you have the cache memory which tries to basically the idea is that you have got a very fast memory, but on the other hand the main memory or the memory in general didn't become fast as in the same pace as the CPU. So therefore, what you have is you have got a cache memory which tries to bridge in this time differences, and therefore what in general happens is that if there is a cache hit, then the access time is less and the power consumption is less. On the other hand, if there is a cache miss, then the access time is more and the power consumption is more. So that implies that you would typically in the computer architecture try to improve the cache hit so that the data is largely found in the cache memory and you don't really need to go into the slow memory. But you can also observe that the adversary, if it is able to properly time and try to distinguish between two accesses, the timing difference of two accesses, then it can figure out whether there is a cache hit or whether there is a cache miss. Now this can lead to trivial leakages of the secret keys. So in order to illustrate this, I will just show here a very famous attack which is called as in the popular name of what is called as prime and probe attack, where a spy first comes in and fills up the cache memory with some garbage data, and then the access is given to the target encryption, which is in this case an AES. Now, when the AES comes in, it basically accesses certain portions of the cache memory, and therefore, right, it basically evicts some data from the cache. Now, if the handle comes back to the spy program, then the spy program starts timing its own access. Then you note that this data is being is being kind of evicted from the cache, and therefore, what we will expect is that these accesses will have got more time, and that is because of the fact that there has been cache misses. So, the adversary can distinguish between cache hits and cache misses, and that can reveal to the adversary the footprint of the AES encryption. So, the adversary can know where exactly the encryption accessed, and that can lead to trivial leakages of the key, as we will see in our subsequent classes. So, therefore, in general, microarchitectural attacks target our present day computer architectures, because our present day computer architectures have been fundamentally designed with performance as a design criteria. Security has always been an afterthought. For example, recent days there has been a famous attack which is called as Spectre and Meltdown, which essentially showed that what they targeted was an optimization technique which is called as speculative execution, where a computer system performs some task that may not be needed. For example, a branch. For example, a branch is because because there is in a pipeline processor, because of a branch, there is a significant amount of penalty that needs to be incurred if the branch fails, and therefore there is an artifact in computing architectures which are called as branch predictors, which tries to predict whether a branch should be taken or not taken. So, these kind of artifacts, which are in general called as speculative executions, are targeted by these attacks which are called as Spectre and Meltdown. But you can observe that since these design principles are so deep rooted in our present day architectures, that suddenly changing them is a really hard task. So, again, to quote Bruce Schneier, fixing them either requires a patch that results in a major performance hit, or is impossible and requires an architecture, a re-architecture of the entire CPU, which is kind of infeasible. And what is probably more surprising is that it took so many years to discover such kind of attacks. On the other hand, security can be a game changer. This diagram shows how the stock hit Intel, for example, when there was this discovery at the beginning of this year, and it shows that the Intel stock fell significantly. For example, the Intel share went down by nearly around 5%, and therefore it shows that security vulnerability can indeed be quite costly. So, therefore, right, it brings us to the fact that we need to make security as an important design criteria, and hardware security has got, although it's new in terms of its discovery and in terms of its existence in literature, it's quite recent in that context, but still it has got profound influence on the modern day world. Hardware provides us opportunities for accelerating cryptographic operations, but at the same time our architecture, or the present day architecture, has been fundamentally developed with performance in mind, and therefore there are significant flaws which can be targeted by adversaries, and therefore what we need proper design for security guidelines to ensure that our hardware does not only give us performance but is also secured. So, with this I would like to thank you.